Hello, I welcome you all in this presentation related with the subject fundamentals of the manufacturing processes, and we are talking about the methods used for improving the properties of the bulk materials and under the heading of the heat treatment. So, we have talked about the three types of the heat treatment processes, namely annealing, normalizing and quenching, or it is also termed as hardening. Since the hardening is one process, hardening or quenching is one process where a thermal transformation takes place from austenite to the martensite. This is the diffusionless transformation leading to the increase in hardness, and in this process the change in crystal structure from FCC to the BCT, body centered tetragonal structure, takes place, and greater is the so this BCT is basically the distorted version of the BCC. So greater is the distortion or the lattice strain induced due to the forced supersaturated solid solution of the carbon in iron. Greater is the lattice strain experienced by the martensite, and because of which there will be greater increase in the hardness as well. But as I have also discussed in the hardening, that tensile residual stresses are developed at the surface. It causes increase in hardness, but increase in hardness is also coupled with the reduction in toughness as well as ductility. So for many applications, if there is a loss of toughness and ductility, then the steel component heat treated for hardening by hardening treatment cannot be used for the many engineering applications, despite of having very good hardness and strength. Therefore, it becomes important to deal with the increased hardness and increased brittleness by reducing the residual stresses, and reducing the hardness marginally, while inducing the toughness and ductility, increasing the ductility. So this is the goal of the tempering. So when the steel after the quenching is subjected to the tempering operation, it reduces the residual stresses, marginally reduces the hardness, marginal reduction in strength is also observed, but at the same time the improvement in toughness and ductility is observed, because hardening leads to the significant reduction in toughness and ductility, which may lead to the abrupt failure under the impact conditions of the hardened steel. Therefore, to induce some extent of the ductility and toughness, tempering treatment is carried out. So basically it is tempering. Normally the quenching and tempering are the couple words. After the quenching, normally the tempering is carried out. So tempering is done in the three different ways. Basically it is also a thermal treatment wherein exposure is given as per the purpose, as per the requirement of the properties, as per the kind of compromise that can be made with regard to the hardness and improvement in the toughness required. Tempering is done in the range of the three temperatures, like it may be heating up to the 250 degrees centigrade, then another is heating 350 to 500 degrees centigrade, or heating from the 500 to the 650 degrees centigrade. So these are the three temperature bands in which tempering can be performed, depending upon the kind of compromise which can be which will be acceptable with regard to the reduction in hardness and improvement in the toughness. So if we see, in order to understand this in better way, if we see the relationship between the tempering temperature at which it is held and the kind of variation in the hardness as well as the toughness which is observed. So toughness normally in joule, and the hardness is measured in terms of the, like say, HRC. So in general, for simple plain carbon steels, there is a continuous drop in the, so like say the 200, 400, 600, 700. This is the kind of temperature say, and the temperature scale in the x-axis and the property variation in the y-axis in terms of the hardness and the toughness. So if we see what kind of the changes in the hardness and toughness take place with the increase of the tempering temperature. So what is normally observed, that there is a continuous drop in the hardness of the steel during the tempering. Say 60 or 65 HRC hardness is realized after the quenching, then during the tempering there is a continuous drop in the hardness with the increase of the tempering temperature. So depending upon the kind of the hardness required and the extent of the drop is acceptable, here it may be like say the 20 HRC, and on the other hand there is a continuous increase in the toughness like this. So this kind of the increase in toughness is observed for the plain carbon steels. So here the toughness will be increasing and the hardness will be decreasing. So as per the combination of the improvement in toughness and the compromise in ductility, if the marginal drop in the hardness and marginal increase in the toughness is acceptable, then the low tempering temperature is selected, and a significant improvement in the toughness and a greater loss in the hardness is also acceptable, then we go for the higher tempering temperature. So higher tempering temperatures will be leading to the significant improvement in the toughness, but greater loss in the hardness is also encountered. If we consider the another kind of the steel wherein like say some the secondary some carbide forming elements are present, then secondary hardening is also observed, especially 500 to the 600 degree centigrade temperature range. So in that case, if the case is not of the simple carbon steels, but if it is related with the alloy steels where carbide forming elements like vanadium, tungsten, chromium, molybdenum are present, then these elements at a higher temperatures start forming their carbides, and which in turn improves the improves the hardness. So for the secondary for the steels, for the alloy steels with the carbide forming elements, the variation in the tempering temperature versus hardness and the toughness, this variation is found to be like initially it decreases because there is no formation of the carbides, but subsequently at higher temperatures the secondary hardening starts. So this the second peak that is obtained corresponds to the like this is corresponding to the 500 to about 600 or 650 degrees centigrade. Before that, since there is no formation of the carbides, secondary carbides, therefore it leads to the drop in the continuous drop in the hardness up to some temperature of say 450 to 500 degrees centigrade. Similarly, the improvement in the toughness, if we see improvement in the toughness is continuous, then it gets flattened, means there is no major change in the hardness, or even there may be marginal the drop in the hardness can occur due to the formation of the secondary carbides. So depending upon the kind of steel being used for that after the hardening, which type of the steel is being tempered, we get the variation in the hardness as well as the toughness as a function of the tempering temperature. What happens during this process, that is what we need to understand. We know that during the quenching, austenite gets transformed into the martensite through the diffusion-less transformation process, diffusion-less transformation, or this is also called a thermal transformation, wherein there is no time for diffusion to take place. So whatever carbon wherever is present in the austenite, that will be leading to the formation of the supersaturated solid solution of the carbon with the iron in form of the BCT martensitic structure. Since the martensite is the supersaturated solid solution, saturated solid solution of carbon in iron, so as soon as it is heated to the high temperature, the excess carbon starts getting diffusing out. So the diffusion of the carbon from the martensite leads to the this will be reducing the lattice strain of the BCT structure of the martensite, and the diffused carbon starts reacting with the iron to form one type of carbide, which is called epsilon carbide. This is basically Fe2.4C. This is also iron carbide, but it's not 6.63% carbon, and it's not iron carbide basically, Fe3C. It's not the cementite, but it's a different kind of the iron carbide, which is known as epsilon carbide, which is formed as a result of the diffusion of the carbon and interaction of the carbon with the iron. So martensite with the reduced lattice strain is formed during the heat treatment process. So depending upon the tempering temperature, the extent of the diffusion of the carbon from the martensite will be occurring. If the tempering is done at the too high temperature, then martensite finally will be forming the ferrite plus the epsilon carbides, and if further prolonged, the tempering can lead to the spheroidization. So this will be simply leading to the softening of the steels. So the purpose of the simple tempering is to reduce the residual stresses, increase the ductility, increase toughness with the marginal drop in the hardness and strength. So this is invariably carried out in all hardened and quenched steel samples in order to improve the ductility and improve toughness. There are two additional type of the special heat treatment processes. These are called Oss tempering and Marr tempering, and both these result in very good strength, ductility and the toughness in the steel, and also the extent of the residual stresses being developed due to the hardening and quenching, they are also reduced significantly when Oss tempering is carried out. So we will see the basic principle of the Oss tempering. In Oss tempering, basically the steel is heated to the fully austenitic, homogeneous austenitic state, and if you see the transformation diagram like this, we are aware of the triple T diagram, like or isothermal transformation diagram. It goes in like this, wherein we have this as MS temperature, and this is as MF temperature, and this is the nose, and here we have the coarse perlite, here we get the fine perlite, here upper bainite, and here we get the lower bainite. Our lower bainite is basically the fine bainite, which results in the insignificant hardness and strength, like 50 to 60 HRC, 40 to 50 HRC, 30 to 40 HRC, and 20 to 25 HRC. This is the kind of variation in the hardness, and here it will be leading to the 60 to 65 HRC for the martensitic, for the hardness due to the martensitic transformation in the steels. So now if you see, if the steel is directly heated to the austenitic temperature and then it is cooled at very high rate, so that it is able to bypass the critical cooling rate and nose off the triple T curve, and then it will be leading to the transformation below the MS temperature, and transformation will be completed into austenite. So here complete austenite to martensitic transformation will be taking place, but this leads to the significant increase in hardness, increase in strength, but at the cost of the toughness and at the cost of ductility as well. So this also induces the residual stresses, tensile residual stresses in case of the through section hardening. steel. So this is not favorable in the sense further high cooling rates also increases the distortion tendency and cracking of the steels. So in order to overcome these issues related with the simple hardening, what is done is steel is quenched from the homogeneous austenitic state to the temperature just above the MS temperature. So say the bath is kept, if MS temperature is 300 degrees centigrade, so at 350 degrees centigrade bath is kept and the sample is quenched in the bath kept at above the MS temperature, and then it is held for sufficient time. So whole of the section will be homogenized with regard to the temperature, and then it will be transforming into the lower bainite. So austenitic transformation austenitic transformation to the lower bainite occurs in case of the aust tempering, and thereafter once this transformation is complete, it is cooled down to the room temperature. So there are two beneficial aspects related with the aust tempering. Quenching means quenching in bath at temperature above the MS temperature, holding at that temperature, holding at the temperature above the MS temperature till austenite transforms into the lower bainite. So this leads to the homogenization and transformation occurring in across the section as a function of time without differential cooling rates being experienced by the component at the surface and at the core, and because of this what we find that the residual stresses, distortion tendency both get reduced, and since it is the lower bainite which is formed, so it leads to the significant increase in hardness but without much drop in the toughness and the loss of the ductility. So there is no major drop in the toughness and ductility with regard, while the significant increase in hardness is realized through the bainitic transformation. So when the bainite is formed, we get very good strength, very good hardness, at the same time toughness and the ductility are also good, means these are not compromised very badly in case of the aust tempering. And the uniformity of the temperature across the section is basically responsible for reduced residual stresses and reduced distortion tendency in case of the aust tempering. Now the next treatment is the Marr tempering. In case of the Marr tempering also, the triple T diagram is used like this: MS temperature, MF temperature, temperature, time, perlite start, perlite finish, coarse perlite, fine perlite, upper bainite, lower bainite. So in this case what is done basically then after the homogenization of the austenite, means after heating the component to the high temperature for sufficient time, the steel is homogenized, and then it is quenched in a bath kept at above the MS temperature. Once it gains the uniformity in the temperature, then it is quenched in the another bath kept below the MF temperature. So basically in this case the quenching happens in this is a two-stage quenching, where in one stage the temperature is above the MS temperature, in the second stage it is quenched in another bath kept at the temperature below the MF temperature. So this reduces the severity of the quenching severity of the quenching is reduced, because quenching is not directly from say 800 degrees centigrade to the minus 10 degrees centigrade, but in this case quenching is first done from 800 to 300 degrees centigrade and then 300 to the minus 10 degrees centigrade. So this basically reduces the differential cooling rates being experienced by the surface due to the drastic quenching from 800 degrees centigrade to the minus 10 degrees centigrade. So when we use the two-stage quenching, it helps to have the better uniformity across the section and reduce the differential rate of the cooling at the surface and the core, and because of this it reduces the residual stresses as well as the distortion tendency is also reduced. So in the second stage quenching, when the sample is taken out and quenched in a bath at another in another bath, then the transformation from austenite to the martensite will be taken, and after holding at this temperature, then sample is again subjected to the heating to the high temperature. So this again holding is done basically for the tempering purpose. So the tempering of the component after the Marr tempering is facilitated. So during the tempering, what will be happening basically, there are two things which will be happening: martensite which has been formed, supersaturated martensite which has been formed, this will leading to the formation of the tempered martensite by rejecting some of the excess carbon from it, as well as whatever is the retained austenite. Retained austenite will be converting into the more stable phases like the perlite and the benite. So these are the two additional benefits wherein the retained austenite gets the stable phases in form of the perlite and benite, as well as the tempered martensite is formed, and both these leads to the improvement in ductility, improvement in the toughness, reduced residual stresses and reduced distortion tendency. So this way the two-stage quenching in the Marr tempering basically helps to improve the mechanical properties, reduce the residual stresses and reduce the distortion tendency in the steel. So this is how now we are completing overall processes related with the heat treatment. I will summarize with this presentation. In this presentation I have talked about the three types of the tempering processes. One is the tempering which is carried out after the hardening, which is basically to induce the residual stress, to reduce the residual stresses and induce the hardness, improve the toughness without causing much loss of the hardness. Then other two heat treatments like Ost tempering and Marr tempering. Ost tempering is carried out by the transformation of austenite into the benite, that is lower benite, which results in the improved hardness, improved strength without much loss of the ductility and toughness, as well as very fine benitic structure is produced, residual stresses are also reduced, and the distortion tendency is reduced. While in case of the Marr tempering, we use the two-stage quenching where austenite is first quenched in the bath, kept at above the MS temperature, and then quenched in another bath kept below the MF temperature. So this kind of the treatment helps to reduce the residual stresses, reduce the distortion tendency, while improving the mechanical properties in terms of the hardness, toughness and the ductility. Thank you for your attention.